Another way of calculating delta H or enthalpy is through Hess's Law. Hess's Law states that when going from a particular set of reactants to a particular set of products, the enthalpy change is the same whether the reaction takes place in one step or a series of steps. Remember that delta H or enthalpy is a state function, and so that's why this is true. If you reverse a reaction, then the sign of delta H is going to reverse. If you double a reaction, then the delta H will double. Here you're given a reaction with an enthalpy of negative 251 kilojoules. If you compare it to the next reaction, you'll notice that they're related. The products are now reactants and the reactants are now products. So the reaction was reversed. When a reaction was reversed, remember delta H is reversed. So delta H is now at positive 251. So instead of releasing 251 kilojoules, it has to absorb 251 kilojoules. If you compare the first and third one, you'll notice that everything was doubled. So delta H is doubled. But we didn't reverse it, so it should be a negative 502. In this reaction, we want to go from graphite to diamond. They gave us the enthalpies of combustion for graphite and diamond, and they want to know the delta H for the conversion. So the first thing we're going to have to do is write the reactions for the combustions of graphite and diamond. So you have carbon graphite plus oxygen yields carbon dioxide. Our delta H for that is a negative 394. Same thing for diamond. Except that's a negative 396. We want graphite as a reactant and diamond as a product. So we're going to have to reverse this second reaction. Which reverses the sign, and we cross out the equation that we changed so we don't accidentally add it at the end. Anything that's on both sides of the reaction can be crossed out. So we have C graphite to C diamond, so everything else should cross out, which it does, and now we add our delta H's up, giving us 2 kilojoules. This one's a little bit more complicated because we have 4 reactions that we're going to have to manipulate to get that top equation. When you're dealing with this many equations, always start with the equation that they gave you. You're trying to find the delta H of that, so we want 2 borons. We have 2 borons in A, and that's the only place we have them, so we can't touch A. We need to leave that equation alone. Next, we have 3 hydrogens as a reactant. The only place we have hydrogen is in C, but we only have 1. And it's a reactant. So we're going to have to multiply C by 3. When you multiply, everything has to be multiplied by that number. Make sure you put your state symbols, especially for things like water, where in D we have water liquid and water gas. We multiplied the equation C by 3, so we had to multiply delta H by 3. Finally, B2H6, we only have in B. We want it as a product, but we have it currently as a reactant. So we have to manipulate equation B and reverse it. When we reverse the reaction, our sign of delta H is also going to get reversed, giving us 2035. Everything else should cross out at this point. And we forgot our state symbol there, so that should be a gas. We have 3 H2O gas, and on equation D we only have 1 H2O gas. It's in the correct location, but our H2Os aren't going to work out unless we multiply it by 3. So in equation D, we multiply that one by 3, everything else has canceled out. And so our delta H is the sum of those 4 numbers. Make sure that if you started with 4 equations that you add up 4 numbers at the end. Not 5, not 3. And you get 36 kilojoules. So this is an endothermic reaction. Go ahead and pause the video and try this one on your own, restarting when you have it. You should have got an A. If you got A, then you can fast forward to the next problem. If you didn't, then let's see where you went wrong. We have silicon tetrahydride, and we have it in the first reaction as a product. We want it as a reactant. So we need to reverse the reaction, which reverses the sign of delta H. Oxygen is next, but we have that in more than one location. So I would save that to the end. So silicon dioxide we have as a product, and in equation 2 we have it as a product. So we can't touch that one because it's already in the location and the number we want. And finally waters, we want 2 as a product. So in the third equation we have it as a product, but we only have 1. So we need to multiply that whole equation by 2. Make sure everything else cancels out and that we're left with 2 oxygens like we wanted. So we have 2 oxygens on the reactant side, so those add up to give us the 2 that we wanted. And our hydrogens also cancel out. So we add the 3 equations up. And that's how we got negative 1429 kilojoules per mole. Go ahead and pause the video and try this one on your own. Restart when you have it. This one was a little bit trickier. The answer was B, but it didn't want to know what the delta H of the equation was. It wants to know how much heat would be given off if 56.08 grams of calcium oxide react. Well, 56 grams of calcium oxide equal 1 mole, so it just happens to be that when you find delta H, that is the answer, but only because 56 grams equal 1 mole of calcium oxide. Had they given you another gram amount, you would have had to do stoichiometry after you got your delta H. So if you didn't get negative 754, let's see how we did that. We have calcium oxide as a reactant and we have it as a product. So we have to reverse the first reaction. Then we have sulfuric acid as a reactant, and we have it as a product in the fourth equation. So we need to reverse that fourth equation. Now we have calcium sulfate as a product, and we have calcium sulfate as a product in the second reaction. So we're going to leave that equation alone. And then we have water as a product. And in the third equation, we have water as a product. So we're going to leave that equation alone as well. Cross things that are on both sides to make sure everything else crosses out. They do, so now we can add our delta H's up. And again, that's 754 kilojoules per mole, and we had 1 mole of calcium oxide.